All right, in this example, we're going to prove a fact about congruences, so modular congruences. So modular classes, you might say. There's many different names here, congruence classes, all kinds of different names for this. But let's start, as always, we'll start our proof here. Let's start by just unpacking the definitions here. I'm going to write this proof with more symbols, so not as many long sentences, but since A is congruent to B, mod n, what does this mean? Well, this means that by definition, right, that by the definition in our text at least, this means that n divides the difference, b minus a, right? And we know what divides means. So this means that there exists, let's say, some integer k in z, such that, what? b minus a is equal to k times n. All right, so there's the consequence of A being congruent to B. We can do the same thing with C and D now, right? So we can say similarly. So similarly, since C is congruent to D modulo n, this means that n divides the difference D minus C, and there exists, we need a different integer here, but there exists some integer m, we'll say, in Z, satisfying what? Now, D minus C is equal to M times N. All right, and then based on what we want to prove up here, we see we have these two statements. We want to say something about the addition of the terms on either side of the congruence equivalence, and so one way to get something like this, one idea, is to just add these two up, right? So we have actual equality here with actual integers. So we can add these two equations and see what happens, right? Adding these equations, what happens? We get that b minus a plus d minus c is equal to k times n. I'll just do this in many stages, right? K times n plus m times n. All right, so on the left-hand side, we can regroup this, right? We can write this as b plus d minus a plus c, just factor and rearrange. On this side, we can factor out the m and the k. So we have k plus m times n. All right, and so therefore, what does this mean? So this means that n divides the difference of these two, right? Just by our definition of divides. And this is true, you don't always have to write this fact out, right? But k plus m is an integer. That's the key here, right? It's one of the keys here. The integers are closed under addition in this case. So thus, what does this mean? This means that n divides this difference. So b plus d minus a plus c. And then just unpacking our definition of the modular equivalence, going the other direction now, so going back this way, right? What do we get? We can say, therefore, a plus c, so that's the thing on the right-hand side of the subtraction, the way we've written this, right? So a plus c is congruent to b plus d modulo n. All right, so this has been proved now. This is the addition property of this modular arithmetic. The addition, it works, right? Addition is closed. And so we did this just by using the definition of congruence with definition of divides here. You could write this out in terms of remainders as well. So you have to prove a couple of things about remainders, but once we've done that, so I'll assume that you've read through that in the notes, but once you have some theorems about the remainders of these numbers, a, b, c, d, modulo n, so when divided by n, then you could write this whole proof in terms of just the remainders if you wish, but that's not how we did it this time. This time is just by simply applying the property divides and the divides definition of congruence classes.